All right, this is our last topic to cover in chapter 6, or excuse me, in chapter 7. This will wrap up the second unit in vectors for us. We still have one more to go. What we're looking at today is just some applications of the dot product and the cross product, how we can use them for a couple of things. One of the ideas is a torque question, which we'll see first up. And this is sort of the idea. It talks about this idea of being able to apply pressure to things and how it makes a difference how far away you are from an object when you're applying the force. So this one here talks a little bit about a train example. The one that I'd usually show you in class involves a door. So if you imagine walking up to a door, the door handle is always on the side of the door that swings open, right? So if you turn the handle and push the door opens fairly easily. But the door handle is a long way from the pivot point. Pivot point would be the hinges. If you tried pushing the door, not near the handle, but rather near the hinges, it's really hard to open the door because the pressure that you're applying is then so close to the hinge, so close to the pivot point, that no matter what force you're applying, it doesn't make as much of a difference. So that's one of these examples of it's much easier to apply pressure in different places. With a wrench, it's much easier to turn a wrench if it's longer. If it's very small, it's harder to get the same pressure on things. So applications of dot product and cross product. We're looking at 2 today. Here's our torque. And torque, it might be something you've looked at in physics actually a little bit. We're going to do just one type of question really with it. We're using the Greek letter tau, so it's just sort of a lowercase t looking shape. And it's a measure of the force that's causing something to rotate. So the easiest type of example for us to do is a wrench turning a nut. And that's what we're going to look at here. It says torque is the cross product of the force applied and the torque arm. The torque arm is basically the length of whatever you're turning. So I've got it there as an R. So we're thinking of it as the radius. Because if you were going to spin a wrench, if you spin it all the way around, the wrench itself would act as the radius of the circle that you're creating. So we're writing the formula there. It says torque is equal to R cross F. Okay, so R is representing the arm, and F is representing the force that we're applying. And the order is important there, and we're going to see why in a second. So R cross F. The way we'll calculate this, because we're going to do everything, in this case, geometrically, so we're not worried about using components or anything. We're going to see a picture for this. Oh, I'll show you really quickly. It's going to look like that. Okay, so we're going to see a picture. What we need to be able to do is calculate the magnitude and the direction. Well, we knew that the formula for calculating the magnitude of a cross product was this. And the way we calculate the direction geometrically was we used the right-hand rule. Okay, so that's how we're going to go about answering this question. So here we are. It says a wrench tightens a bolt as shown. Determine the magnitude of the torque. So I'm going to just write that formula down again really quick. Torque was equal to the arm cross the force. So here's our picture over on the right. We have our wrench. It's turning. It's not a bad picture. You can see what's happening. We're grabbing that handle, and the force is being applied downwards in this case, right? We're trying to. Whoops, that's not very straight. We're pushing this way on the wrench. Okay. So for us to calculate this, it's actually not too hard. We're going to get the magnitude first. So the magnitude of the torque is the magnitude of the cross product. And the way we calculate the magnitude of the cross product was we did magnitude of the first vector, magnitude of the second vector, times the sine of the angle in between. Now, the only thing we have to be a little bit careful of, the angle in between. The angle always refers to if the vectors were aligned tail to tail. And these aren't. These are aligned head to head, which is completely wrong. So what the easiest way to do it is I'm going to just take this vector, slide it down there. And here's the other one if I slide it over. So this guy here is, this is vector r, and this is vector f. Sorry, vector r is now looking an awful lot shorter because I ran out of space. But now they're aligned tail to tail, and we need to know that angle there, and conveniently it's also 80 degrees. Those are just opposite angles, right? The 80 going straight across that angle. So it turned out it was 80 anyway, but it's something that we needed to be careful with. So to calculate this, the magnitude of the radius. Now, one thing I better back up for a second because something I skipped over and I shouldn't have. It said torque is measured in Newton meters, and what's important there is the meters part. That's the way we're going to measure this force. But in the example, we're given the radius in centimeters. So we need to make that conversion into meters. 20 centimeters is the same as 0.2 meters. So be careful there. It's honestly, it really does become almost something that's just designed to see if you're paying really close attention. Magnitude of the radius is 0.2 meters. The magnitude of the force that we're applying is 60 newtons times sine of 80. And I got 11.82-ish Newton meters. Okay, that's how we calculate the torque. Magnitude of the torque. The direction. Well, this is where it was important, the order that we wrote it in. That's written as R cross F. So to get the direction, remember in this case, the direction is either going to be into the board or out of the board, or into your paper, out of the paper. And what we did was we used the right hand rule. So you use your right hand, and you have to point the fingers of your right hand along the first vector. So they're going to point along vector R here, and then you need your fingers to curl through the 80 degrees towards vector F. And in this case, the only way you can do that is if your thumb ends up pointing into the board. So if you try, you really should try this on your piece of paper. You got to point your fingers along vector R. When you do that, your thumb will point into the board, and your fingers should curl right through the 80 degrees and point towards vector F. So the direction, in this case, it's the direction your thumb points, would be into the board or into the paper, however you want to say it there. And if you think about what that means that the nut at the center of that wrench is going into the board. It's being tightened. So if you've ever tightened something like this, you know that if we turn that wrench in that direction, that should be tightening the bolt, and that's what's happening here. Okay. Our second application, we're just doing two today, so torque was one of them, and this is our other. It's a fun word. It's called the volume of a parallelepiped. Kind of a bizarre shape, actually. It's not a shape that you'd see very often. It's a little bit tricky to describe, I suppose. What you see there, it's drawn not too badly from a three-dimensional standpoint, I suppose. Every side is a parallelogram. So maybe the easiest way to picture it is if you had a parallelogram for the base. Okay, so you're just think of the base here as being a parallelogram. And then instead of the shape going straight up like a box would, the sides actually tip a little bit. And that's what's creating this parallelepiped shape. So considering it's a pretty random shape, we actually have a relatively easy way of calculating the volume. The way that it works is you just have to do the area of the base times the height of the shape. Now, height's always tricky, right? Height would be the height going straight from the bottom all the way to the top. So a line like that. That would be our height. So area of the base times the height will give us the volume. So as I say, this actually works out really, really nicely. We just said that the base was a parallelogram. And one of the things that we knew about the cross product was that the magnitude of the cross product gives you the area of a parallelogram. So I've got vector u and vector w on the bottom there. If I do u cross w, and then the magnitude of that vector would represent the area of the parallelogram. That's the base, and that's just defined, right? That's something that we defined the cross product to be. The height's a little bit trickier. Here it is drawn in for you. And for that height, what I did was I introduced another angle there. That's angle alpha. And alpha is going to be that angle right in between vector v and the height. So remember, this is a three-dimensional picture, but angle alpha is that angle between vector v and the height. And what I want you to notice is that alpha is the same in those two places. So I have alpha here, and I also have alpha here. And that's just the Z pattern, right? If you tip your head to the side, you can see the Z pattern a little bit better. The blue line and the red line are parallel. So those two angles in the corner have to be equal. So the way I can calculate the height, let me backtrack, I suppose, just a second. If we had done this, cos of alpha, pardon me, cos of alpha is equal to the adjacent over the hypotenuse. So the adjacent for alpha is the height, and the hypotenuse would be the magnitude of vector v. And then all we've done is we've rearranged that for the height to get this formula, multiply both sides by the magnitude of v. So I've got a way of calculating the area of the base. I have a way of calculating the height. So I can sub that in here. Area of the base is just the cross product, the magnitude of the cross product, I should say. And then the magnitude of vector v times cos of alpha. And here's the neat part. I don't think it's obvious as you just look at that. But remember what the definition of the dot product was. The dot product is magnitude of A, magnitude of B, cos theta, right? Theta is the angle in between. Well, if you think about what I have here, I have the magnitude of a vector, the magnitude of another vector, and alpha is the angle in between vector v and that cross product. Right? That's exactly the angle I needed. So in fact, the volume is equal to that. Let's light that up a little bit. There we go. So we can calculate the volume of a parallelepiped by doing the cross product of two of the vectors and then dot product that with the third vector. Okay, and that's our formula. You've actually seen that formula before. That was the same formula that we used to determine if vectors were coplanar or not. So that was our test for coplanar vectors. And we said if the cross product dot product ended up being 0, then the three vectors were coplanar. That actually makes complete sense in this case. If vector v, I'm going to redraw it here for a second, if vector v was actually flat on that shape, then there wouldn't be any volume. The volume would be 0. All three vectors are coplanar. So this same rule now works in both cases. Now the only other thing to mention, we're going to try an example next. I've got absolute value marks there. And the reason for that is when you do the cross product dot product, you might end up getting a negative answer. And of course, we can't have a negative volume. So if you get a negative answer there, we're just making it positive to represent the volume. The other little bit of good news, the formula there says U cross W dot V. Remember, same with the coplanar test before. It didn't matter which vectors you pick. It doesn't matter what order you do it in. So if I want to do U cross W dot V, that works. But if I want to change the order up, that works fine too. So here's our example. It says parallelepiped is defined by vectors A, B, and C. Determine the volume of the parallelepiped. So the volume is equal to the absolute value of the cross product of two vectors dot product with the third vector. Now what I want you to notice, I just finished saying the order doesn't matter, but we're going to have to do the cross product first. And remember, it's much easier to do the cross product with zeros in it. So we're going to be better off doing A cross B first, and then dot product that with vector C. You'll get the same answer no matter what you do, but this is going to make the calculation a little bit easier because vector A and B have zeros. So this is a side, A cross B. So to do this calculation, we're now using our components. So I'm going to write down our numbers. This is for our cross product trick. 0. And remember how we did this? This was our down product minus up product. So 7 times minus 5 is minus 35. Take away 0. What's this? 0 times 2 is 0. Take away minus 15, so plus 15. And then 3 times 0 is 0. Take away 14. So there's A cross B. I can maybe fill that in back here now. It's going to be the magnitude of A cross B is minus 35, 15 minus 14. And then I have to dot product that with vector C, which is 461. So I'm gonna leave those absolute value signs out. Remember, those are actually representing absolute value this time, not magnitude. Because when I do the dot product, I'm just gonna get an answer, and I'm gonna get a number. So to do the dot product now, it'll be minus 35 times 4, which is, I think, minus 140. 6 times 15 is 90. And then minus 14. Oh, good, we are going to get a negative on this one, too. If we put that all together, minus 64, I think. Pretty sure it's minus 64. But we're taking the absolute value of that. So the volume is just 64. There's no units here, right? It's 64 units cubed, I guess we could say. We were never given centimeters or inches or whatever, but we often aren't. So that's a relatively easy calculation to get that volume of the parallelepiped. One cross product and one dot product, and we get it. Again, keep in mind that this really is exactly the same calculation as our test for coplanar vectors. If we could have done this question the other day, and I could have said, the question would have been, here's vector A, vector B, and vector C. Determine if the vectors are coplanar or not. We would have done exactly the same thing. We would have got an answer of minus 64. And our conclusion then was, since it wasn't equal to 0, the 3 vectors we started with are not coplanar. Now we're just adding a little bit more to it and noticing that the number answer we get actually corresponds to the volume of the parallelepiped formed by the vectors. Okay. And that wraps up chapter 7. So that's all of the material now that you'll need for our test for chapter 7.